Every token an LLM generates feels tiny. It is just one more word, one more fragment of code, one more answer. But inside the GPU, that token is expensive, not only in arithmetic, but in memory movement. When you ask why generation pauses before the next token appears, the answer is not just that transformers do a lot of math. The deeper answer is that modern AI keeps crashing into a classic systems bottleneck, the memory wall. Compute has grown absurdly fast, memory capacity has improved, but memory bandwidth and access patterns still decide how quickly a model can actually serve you. In 2026, this has become the secret bottleneck of practical AI. The frontier is no longer just bigger models. It is how efficiently we move keys, values, activations, and attention state through limited VRAM. And that is why two ideas changed inference economics. KV caching, which lets the model store the past instead of recomputing it, and PagedAttention, which borrows paging ideas from operating systems to keep long context windows from suffocating GPU memory. If you understand those two techniques, you understand why modern LLM serving suddenly got faster, cheaper, and capable of million token context windows. To see the problem, we need to look at attention the way the hardware sees it. For every token, the model builds a query vector and compares it against key vectors from prior tokens. That gives us attention scores, and those scores decide how much of each value vector should contribute to the next hidden state. Conceptually, this is elegant. Operationally, it is brutal. As the sequence grows, the attention map grows roughly with the square of the context length. Double the sequence, and you do not merely pay double. You expand the surface area of interactions. On paper, that sounds like a complexity lecture. On the GPU, it looks like a room filling with boxes until the door can barely open. We have model weights occupying a fixed chunk of VRAM. We have activations for the current step. We have temporary workspace for kernels, and we have attention state that keeps growing as more tokens arrive. This is why long prompts and long generations feel so much heavier than they look. The model is not just calculating the next word, it is revisiting a growing history and pulling more data through memory every step. The arithmetic units often have more work available than the memory system can feed efficiently. That is the memory wall in practice. The GPU is full of potential compute, but it keeps waiting for memory traffic to catch up. And if you push batch size, prompt length, or concurrency too far, VRAM fills to the point where latency spikes, throughput collapses, or requests fail outright. KV caching fixes the waste. During autoregressive decoding, the old tokens are already known. Their key vectors and value vectors do not change. So instead of rebuilding them for every new token, the inference engine stores them once in a cache. Then, when the next token arrives, the model computes only the new query, key, and value for that frontier token, appends the new key and value to the cache, and attends over the stored history. This sounds almost obvious once you say it out loud, but the impact is massive. Without a cache, the model keeps reprocessing the past. With a cache, the past becomes a reusable memory structure. That shifts the cost profile of decoding. You still pay for attention over previous positions, but you stop paying to recreate the same key and value projections again and again. In production terms, this improves time to first token after the prompt phase, reduces per token latency during generation, and makes batching more practical because each request carries forward its own compressed history. Visually, I like to think of the KV cache as a bank of matrix blocks sliding out of the active compute lane and into long-term GPU storage. New blocks join at the edge. Old blocks stay parked, ready to be read instantly. The model stores the past so it can focus compute on the present. That is the central trick, and it is why modern decoder inference suddenly became viable at much larger scales. The model is no longer arguing with yesterday's tokens from scratch. It remembers them structurally. But caching alone is not enough at serving scale. Once you have many requests with different prompt lengths and different generation lengths, memory allocation becomes chaotic. Some sequences finish early, some keep growing, some need more KV blocks than others. If you allocate long, contiguous chunks for every request, you end up with fragmentation. Usable VRAM exists in theory, but in practice it is scattered into awkward gaps. This is where PagedAttention changed the game. The idea borrows directly from operating systems. Instead of requiring each sequence to occupy one big contiguous slab of memory, we divide the KV cache into fixed size pages or blocks. Each sequence gets a logical view of its memory, while the runtime maps those logical blocks onto physical GPU pages wherever space is available. That means sequences can grow without demanding a perfectly contiguous region. It also means completed requests can free blocks that are immediately reusable by other requests. Fragmentation drops, memory utilization improves, and throughput becomes much more stable under mixed workloads. The beautiful part is that paging does not change the conceptual model of attention for the user. The model still attends over prior keys and values. But under the hood, the serving engine has turned that history into something that looks more like a virtual memory system than a simple array. That systems trick is one of the reasons long context inference feels radically better now than it did a few years ago. Put the pieces together and the story becomes clear. The future of LLM inference is not just about larger parameter counts, it is about disciplined memory engineering. KV caching cuts out redundant recomputation. PagedAttention keeps the cache flexible and allocator friendly. Together they unlock higher throughput, better GPU utilization, lower latency per generated token, and the practical foundation for context windows that stretch toward 1 million tokens and beyond. That matters for code generation, retrieval-augmented systems, multi-document reasoning, agent memory, and any application where the model needs to keep a long working set alive. If this video helped you see the stack more clearly, subscribe to SyntaxVisual. This channel is for engineers who want the hidden mechanics behind the buzzwords distributed inference, transformer architecture, memory systems, and the design choices that actually move products forward. In the next episode, we can visualize speculative decoding, mixture of experts routing, or how inference clusters schedule work across many GPUs. Until then, remember the real bottleneck was never just intelligence. It was how we fed memory fast enough to let that intelligence speak.